going to examine what correlation is. So correlation measures the strength and direction of the linear association between two quantitative data variables. So you need to have quantitative variables. We're talking bivariate data. The actual letter we use to denote the correlation coefficient is the letter R. And over here you will see the formula found on your AP formula sheet. Most times you'll just use technology to calculate this. We'll do it once in our next lesson by hand so you can see where these values come from and understand it a little bit better. The correlation coefficient is always between or equal to -1 and 1. Now, it's very rare that it's actually equal to -1 or 1. Much more often, it will be in between these two values. So it measures the strength and the direction. So the closer it is to 1 or -1, the stronger that association is. The closer to 0, the weaker it is. We use words like moderately. Kids often want like a cutoff value for when do you say it's moderate or when do you say it's strong. I say just kind of a rule of thumb would be if you kind of go halfway in between 0.5 and 1, so like 0.75 and greater, that's going to be strong. Between 0.5 and like 0.75, we're going to say, that's moderate. I would say like 0.3 to 0.5 you would say is weak, and then almost no correlation if it's less than like 0.3. Okay. Here are some sample scatter plots with the correlation coefficient shown. Notice so this one right here, -0.3 is very weak correlation, but you could say that there is somewhat of a negative association here, whereas this correlation of 0.9 is quite strong, and the fact that it's positive is showing that there is a positive linear association. Okay, here's a sample where you're given bivariate data, temperatures in degrees Celsius, and the corresponding ice cream sales. Must be for some little ice cream shop. Okay, so if you were asked to describe the association, I think you would use words like, I see a fairly strong, positive, linear association. And if you actually calculated your correlation, it actually turns out to be this very high number, close to 1, reinforcing what you are seeing. Now, it is very important that you have linear data when you are looking at correlation, because here's a sample where we continue the same scenario, but it gets so hot that people have stopped walking to the ice cream shop. It's heat wave in town, so people just stay indoors. Is there still an association? Yeah, absolutely. Looks like a pretty strong association as well, but if you actually calculated your correlation coefficient here, it turns out to be 0. And why is that? Because this is nonlinear. So you really need to have linear data when you're talking about a correlation coefficient. Okay, strong association, but not a strong correlation. There's no correlation here. So to emphasize again, correlation is measuring your direction and strength of the linear association between two quantitative variables. So there's 3 conditions you really need to check when you're talking about correlation. First of all, you got to have quantitative data, so we call that the quantitative variables condition. Straight enough condition, meaning it needs to be linear. And then if you have outliers, we'll quickly talk what do you do if you've got some outliers. So your text points out quantitative, it only applies to quantitative variables. Be wary of, remember there are some numbers that are actually categorical, so make sure they're not masquerading as quantitative. And you should always check that you understand the variables units and what they measure. Okay, that's a way to help verify, what are we measuring? Does it make sense to find an average? That sort of thing, to verify that it's quantitative. Second thing is it straight enough? You can only calculate a correlation coefficient if they are linear. You could actually calculate it for any pair of variables, but correlation measures the strength only of a linear association, and you're going to get a very misleading result if the relationship happens to be curved. your outlier condition. So we're going to look, outliers can distort your correlation dramatically. An outlier could make it appear that something that has a very small correlation, it could actually look very large when you do the calculation. Or it could be the other way around. So if there is an outlier, rule of thumb here is it's often a good idea to report the correlations with or without your suspected outlier. Okay, so let's look at an example. Pause the video and read this scenario. Okay, so we are asked to determine is it appropriate to calculate the correlation and explain. So fortunately, you are given a scatter plot. If you were not, you would put your raw data into your graphing calculator and have the calculator generate a scatter plot for you to look at. So I'm going to check my conditions. Well, the variables, yep, they're quantitative. Next, is it linear? Yeah, it looks fairly linear. You could probably draw a line like here. Got this one point here that's looking a little suspicious. So I say, you know what, there may be an outlier at 2.55. So we may want to calculate R, the correlation coefficient, with or without that point. But therefore, it's appropriate to calculate the correlation. And now the correlation's been calculated for you here in Part B. So explain what we have learned about the results of these experiments. So what's this tell me? Well, I see that there's a strong positive linear association. So there's my defs between placebo improvement and drug improvement. And then I'm kind of showing what that means. If the patient shows strong improvement with the placebo, they are likely to see improvement with the drug. So one thing you need to be careful with, though, is don't say that one is causing the other to be true, which is one of our golden rules of stats, that correlation does not mean causation. And let's examine this a little further. There's this fabulous website that you're going to explore, Spurious Correlations, at tylervigan.com. And there's many awesome graphs here. And if you look at this, people who drowned after falling out of a fishing boat is our red curve here. And the marriage rate in Kentucky. Interesting. Notice there is a very similar association here. So does that mean that if I get married, I am going to fall out of a fishing boat and drown, or vice versa? The fewer cases of marriage, it looks like we have fewer deaths, whereas the more marriage cases, the higher amount of deaths. But I think you would recognize that even though these follow some interesting similar pattern, one is not causing the other. And that's our golden rule of stats. We're going to look in a future unit how we prove causation. So scatter plots and correlation coefficients never, ever, ever prove causation, The reason that it may look like there is some sort of correlation, and there is that a hidden variable stands behind a relationship and determines it by simultaneously affecting the other two variables. It's called a lurking variable. So picture some creeper in the bushes that's affecting the two things out in the open. So here's a sample about cellular phones and life expectancy. A survey of the world's nations in 2004 shows a strong positive correlation between the percentage of the country using cell phones and life expectancy. So if it's a strong positive, that's saying those that tend to use a cell phone also tend to live longer. So does this mean that cell phones are good for your health? So this statement really is saying, is one causing the other? You will often be asked this question, and your gut reaction needs to be no. All it's telling you is that countries with a higher cell phone use also tend to have a higher life expectancy. And then here's where you need to put your analytical skills on. Stats is about really honing these analytical skills. What possible variable might explain this strong correlation? So there's not one right answer here. You may think of something else, but something that pops in my mind would be wealth. For instance, those that can afford to own a cell phone, because there's quite a cost associated with that, may have more wealth. And if they have more wealth, then they may also be able to afford better health care, which could be causing them to live longer. There may be other things in the background that are causing this as well. But just citing one possible thing and noting that it could be a lurking variable, which is that hidden variable that's affecting both the ability to own the cell phone and your life expectancy. It just acknowledges you recognize there's something else that is affecting, that could explain the causation part. Okay. Please reach out if you have any questions. Complete the additional activities on Schoology to really understand our correlation coefficient.